Welcome to the second lecture of this week. So today we are going to be completing our time domain analysis for the second order system in underdamped form. So remember, in the last lecture we have actually calculated the analytical form of the response for a second order system in standard form. It is a step response actually, and we have seen that we have a response given like this. So I have my unit step given here, and it is at the same time where the response is actually converging here. So this point is nothing but y infinity for us in this case, and a second order system in standard form would give us a response in this form. Okay, and it oscillates back and forth, and then it converges to the value 1, which is what we call as y infinity. And this is our y of t. And what was this case? This case was the underdamped response. When psi is between 0 and 1, the damping ratio is between 0 and 1. And where are the pole positions? S1, 2, the pole positions were at minus psi omega n plus minus j omega n 1 minus psi square. And remember, we call this number as a damped natural frequency. All right? And if I draw the closed loop pole locations here there is no loop, but I'm still calling the poles as closed loop poles. So we have this circle with radius omega n, and our roots are always on this circle, and the real parts are equal to minus psi omega n, and their imaginary parts are j omega d or j omega n 1 minus psi square. And here I have the imaginary part of the conjugate root that we have. So, and the next thing is this distance is omega n, and remember we have defined this angle, which is as the angle phi here. Okay? And what were the properties of that angle? Its sine so sine phi is equal to, it is the ratio of this distance to the hypotenuse, and it's going to be just square root 1 minus psi square, and cosine phi is equal to the damping ratio itself. And then how can I find this angle phi? What I can do is just take the arc sine of this value or arc cosine of this value. Sometimes we write the tangent phi, which is sine phi over cosine phi, and it is given in this case as 1 minus psi square over psi, and we can calculate also phi as the arc tangent, this value 1 minus psi square root divided by psi. Okay? So this is our angle phi. And now we're going to be making a connection between the time domain quantities, which are the performance measures that we have seen before in the previous lecture, and these pole locations, or these Laplace domain quantities, psi and omega n. So the first quantity that we are going to be looking at is the rise time. Rise time is this time instant, okay? TR is the first time instant that our response intersects the desired value. So the desired value is also at the same time what y infinity is in our case. So I can actually define the rise time as the first time instant at which our response intersects for the first time the value y infinity. And that is going to be our general definition. So even if this response is scaled, even if the second order system is not in standard form, that is going to be our definition of the rise time. It is the first time instant that the response intersects y infinity, the limiting point of this response. So before we start with the derivations, let us remember what we have derived in the last lecture. We have derived the general form of y of t for the second order system in standard form. This is the step response. And what we have derived is in the following form: minus psi omega n t divided by 1 minus psi square. And I have sine omega dt plus phi. This was the response that we have derived. This is true for t larger than or equal to 0. And we are going to use this expression in order to be able to find a relationship between tr and these, which is the time domain quantity, and omega and psi, and the pole locations, which are Laplace domain quantities. So the first thing is going to be related to the rise time. So tr, which is the rise time, is the first time instant that the response reaches y infinity. Okay? That is the definition of rise time. It's the first time instant that the response reaches its final value. So in this case, I can actually write here the equation for the rise time. Y of tr is equal to y infinity. Y infinity is a fixed value, and I need to solve the equation y of tr, which is equal to that fixed value. And in our case, in this case, when we have the standard system in standard form, second order system in standard form, the final value is 1. So equivalently, I can actually solve the equation to obtain the rise time value. So I can solve the equation y of tr is equal to 1. Of course, you might think that there are infinitely many solutions of this equation. Why is that? Because we see that this response intersects this value 1 infinitely many times. And here we are after the first value. Okay? We need to find the first such intersection. Okay? Now let us actually try to solve that equation. So y of tr is equal to 1. That means that here this second term has to be equal to 0 at tr. All right? And if I find y of tr, then I would get 1 minus e to the minus psi omega n tr divided by 1 minus psi square sine omega dt plus phi here. And this thing should be equal to 1 at tr. All right? And instead of t, I'm writing tr here, so that gives me my equation. And here you see that these ones are actually cancelled, and then the second quantity should be equal to 0 at tr. That means that one of these quantities should be equal to 0. The exponential is never 0. Okay? It's always a decaying exponential, and it becomes 0 at infinity. So we don't count that 0 at infinity. This is never 0. It doesn't really matter if this is 0 or not, but this is a non-zero constant always. So the only possibility that this equation can be satisfied is when this sine term is equal to 0. Okay? So the equation for the rise time is given as omega dtr plus phi is equal to 0. I need to solve this equation, and we know that there are infinitely many solutions to this equation, and I need to find the smallest one. And here, phi is an angle between 0 and 90 degrees. So I have this phi here. This phi is between 90 degrees and it is also 0. It can be also 0. But here, let me remove the possibility of 0, because that expression is not valid. Sorry, that definition is valid at psi equals to 0, but it's not valid at phi is equal to 90 degrees. All right? I am not making sense here. So it is valid when phi is equal to 90 degrees, and when it is not valid when psi is equal to, when phi is equal to 0. Okay? So here, because this equation is valid, we have shown that this, when the phi is 90 degrees, this is my undamped response, and I can obtain the undamped response by substituting psi is equal to, psi equals to 0 here. And I know that when phi is 90 degrees, cosine phi is just 0. It's our damping ratio, and then that equation is valid. This equation is not valid when phi is equal to 0, when we have a critically damped system. Because when we have a critically damped system, we shouldn't have any sines or cosines in the response. We shouldn't have any oscillations. Therefore, this expression is not really valid at phi equals to 0 or the damping ratio equals to 1. So now I'm trying to solve this equation. This phi is between 0 and 90 degrees, and TR is a time value which is larger than 0. So if I look at the sine function, so this is time, and the sine function is something like this. This is 0, this is pi, this is 2 pi, etc. So at t equals to 0, the argument of the sine function is phi. So we start somewhere here, which is an angle between 0 and 90 degrees. And as t increases, we are going in that way. And the first time that we hit sine equals to 0 is when the angle of the sine is equal to pi. Okay, or 180 degrees. That means that this TR value gives me this angle value inside the sine, which is equal to pi. So in order to be able to solve for TR, I write this equation. Okay, this is the first time that sine value is equal to 0. And you can see here that if I continue increasing sine, I would get other 0 values as well, but they're going to correspond to the other intersections in this response. So here, if I extract TR from this formula, I would get pi minus phi divided by omega d. Okay? So this is a time domain analysis expression, and it makes a connection between a time domain quantity and Laplace domain quantities phi and omega d, as you see here. So that is going to be our formula for the rise time, and we're going to be deriving formulas for the other quantities that we have defined in the previous lecture. So here we see that the rise time is dependent on this angle of the poles, and it is also dependent on the imaginary part of the poles. So we have a double dependence between TR and these two parameters. So now this completes the analysis for the rise time, and now we are going to go into the definition of peak time. So this peak time where we have the maximum overshoot is called TP. Okay? And now we are going to define and try to find that TP value using a similar type of idea. TP is called the peak time. Is the first time instant that the response makes a peak. Okay? We see that again, the response makes infinitely many peaks. So there is a peak here, there is a peak here, etc. Therefore, if I want to find this peak time among those peaks, I need to choose the earliest one or the smallest one here. So now let us write the equation for this peak time. So what is the equation that is satisfied by the peak time? So here we know that at this peak the derivative of the response should be equal to 0. That means that my equation to obtain Tp from is going to be y of Tp or y prime of Tp. Instead of prime, I can write d over dt y of t evaluated at Tp is equal to 0. Okay, we need to solve this equation, and among all of the solutions, among the infinitely many solutions of this equation, I need to choose the smallest one. So now I need to actually take the derivative, find the derivative of this response. Okay? So here let me take the derivative with respect to time. Instead of d over dt, I will write y prime of t here. That is going to be, the derivative of this constant is 0, and this minus sign is just and this number is just a constant with respect to time, and I have the multiplication of functions of time here. So that means that I will first take the derivative of this function times the second one, and then the derivative of the second function times the first one. Okay? So here is what I'm going to do. I'm going to write this minus sign, and whatever I do, I will take e to the minus psi omega n t parentheses. And there is a constant here which is not disappearing in any way. It's 1 minus psi square. Now let me take the derivative of the first function here. This function, if I take the derivative with respect to time, it is the derivative of the exponent here. It is going to be minus psi omega n times the exponential. But the exponential is already here. Okay? So I don't write anything here. Times the second function. So it is sine omega dt plus phi. And I have plus the derivative of the second function, which is this one, and it's going to be omega d times cosine omega dt plus phi times the first function. But the first function is the exponential itself, which is already here in the parentheses. So actually this completes my derivative expression. And whatever I have to do, I need to equate at the end this function to 0. All right? But before that, I need to make some effort in order to be able to simplify this function. So what was omega d? Omega d is omega n times square root 1 minus psi square. So there is an omega n here, and there is an omega n here. I'm going to be taking these omega n's out, and I will also take a minus 1 parenthesis here to cancel this minus sign. Okay, so it's going to be e to the minus psi omega nt divided by 1 minus psi square, and I will take also omega n parentheses, and I will take minus 1 parentheses. So in general, I'm taking a minus omega n parentheses here. So I have minus, so plus psi sine omega dt plus phi, and plus. Now, since I'm taking a minus omega n parentheses here, this plus is going to turn into a minus, and I would have 1 minus psi square cosine omega dt plus phi. Okay? So now I'm going to be using these expressions. Psi is cosine phi, and square root 1 minus psi square is sine phi. Well, let me write those. E to the minus psi omega n t omega n square root 1 minus psi square. Instead of psi, I write cosine phi, and I have sine omega dt plus phi, and I have minus, I have here sine phi and cosine omega dt plus phi. Okay? Now what do we have here? I have the sine of an angle times the cosine of an angle minus I have the cosine of that angle and sine of the other angle. So this is the formula for sine of the difference of two angles. So if I write sine A minus B, it becomes sine A cosine B minus I have cosine A sine B. Okay? This formula is exactly in this form, and if I use such a simplification on this expansion here, I would get the following. Y prime evaluated at t is e to the minus psi omega n t divided by 1 minus psi square times omega n, and this is just a single sine. Sine, what is the angle A? Angle A is the argument of sine in the first term, omega dt plus phi. And what is the angle B? It is phi, minus phi. And these phi's are actually canceling each other very, very conveniently. And then we are going to get the following result. Y prime of t is equal to e to the minus sine omega n t omega n 1 minus psi square, and simply we have omega dt. Okay? And now what I have to do is to equate this derivative to 0. Then I have to find the solution of this equation, and I need to find the smallest solution of this equation. So here I see that these parameters are all non-zero. So the only possibility for this equation to be satisfied would be sine omega t. Let us now substitute Tp here. Sine omega d Tp is equal to 0. I need to solve this equation. So I see that at t is equal to 0, sine is 0, sine of 0 is 0, and at t is equal to 0, this equation is satisfied. Okay? So is the peak time equal to 0 then? What do you think? In this case, the answer is no. Okay? So when you look at 0 here, when you look at time 0 here, you see that there is not a peak of the response. But here, my drawing here is a little bit misleading, because I understand from that equation that the derivative of the response at time equals to 0 should be equal to 0. So my drawing should be more like the following. So I need to draw this like this. Okay? So this derivative, in this case here, is still 0, and here we have a local minima, not a maxima. We are looking for a peak here, but this is a dip. The first dip of the function is at 0. So we start here with 0 slope, and then the function increases and it makes a peak. So the t equals to 0, or t equals to 0 is not the solution that I'm looking for here, okay? Because at t equals to 0, we have a local minima, not a local maximum. So here, therefore, when is the sine function equal to 0? What is the angle that I need to have? So this is going to be the same angle that we used in the rise time definition, and in this case this angle should be equal to pi, and that is the first time that this equation is satisfied with at a local maximum. Okay, so I have this is equal to pi, and then I can actually extract this Tp from this equation as pi over omega d. Okay. So that is my formula. That is the time domain analysis formula relating the peak time domain quantity to the Laplace domain quantity omega d. Okay? And in this case, compare this with TR, pi minus phi over omega d. We see that Tp is, if phi is actually non-zero, Tp is always larger than the rise time. Okay? So now we're finished with the peak time. Now we're going to go into the so-called maximum overshoot. So the maximum overshoot is this difference, okay? So I have this difference which is given as MP. And if I write MP, then this is called the maximum overshoot. Is the maximum amount by which the response exceeds y infinity. Okay? It is the maximum amount by which the response exceeds the y infinity. Here y infinity is 1, so, and the maximum amount by which this response exceeds this constant here is going to be MP. So if I write the formula for MP, then it's going to be y of Tp, the response evaluated at the peak time, minus y infinity. Okay? This is called the absolute maximum overshoot. Sometimes this response does not go to 1 at the end, and in that case we're going to be interested in the percentage maximum overshoot, and it is defined in the following way: NP percent overshoot is y of Tp minus y of infinity divided by y of infinity. And since I need to give here a percentage, I multiply this with 100%. Okay? So this is the usual formula that we are going to use, because in general we won't know directly if the response is going to be converging to 1 or not. Therefore, we generally do not use the absolute overshoot, but we use the percent overshoot definition. And the good thing is that the formula that we find for the case when y infinity is equal to 1, formula that we find for MP when y infinity is equal to 1, is also going to be the formula for the percent overshoot. So we won't have to change anything when we use percent overshoot here. And all of the earlier formulas that we have found, if the response is scaled, so if we don't have, for example, a second order system in standard form, if the response is scaled, then all of the formulas that we found will be valid. And in such a case, we won't be using the maximum overshoot, the absolute value, absolute maximum overshoot, but instead we would be using the percent overshoot definition, which is much more meaningful in that case. And in our case here, y infinity is equal to 1 in that response. And now let us try to find what the maximum overshoot is. And when I find the formula for the maximum overshoot, for this one, then it is going to be also equal to the percent overshoot, because y infinity is equal to 1 in this case. Okay? But this percent overshoot formula would be always valid, even if we don't have a system we don't have a system in standard form. So now let us find y of Tp first. Okay? I have found what Tp is. It is pi over omega d. It is only related to the number pi and the imaginary parts of the poles here. The imaginary part of the poles is omega d. And what I'm going to do is I'm going to substitute t equals to pi over omega d in this equation, okay, in that solution. So maybe I should make some calculations first. Psi omega n Tp is equal to psi omega n, and Tp is pi over omega d. If I write psi omega n, pi over omega n 1 minus psi square, because this is what omega d is, and omega n's are cancelling here, and that gives me pi times psi over square root 1 minus psi square. Okay, so the argument of this exponential function is going to be minus pi psi over square root 1 minus psi square. And here, what about the sine argument here? Omega d times, so Tp plus phi is going to be omega d. Tp is pi over omega d plus phi here. And here omega d's are cancelled, and that means that the argument of the sine should be pi plus phi. Okay? Now I have calculated everything necessary for me to evaluate the response at Tp, and that is going to give me y of Tp is 1 minus, so here I would have e to the minus pi psi over square root 1 minus psi square. I have already calculated that thing. Divided by square root 1 minus psi square, and I would have sine pi plus phi. Okay? When you have an angle phi, and when you look at its sine value, what would be the value of sine of the angle phi plus pi? If you add an angle 180 degrees, what would happen to its sine? So I have the angle phi here. It is between 0 and 90 degrees. Is this one. What would happen to the sine value of this angle if I add to it 180 degrees? This is going to be actually negative sine function. So this is equal to minus sine phi. Okay? And that is going to give me 1 minus. So this minus sign is going to be cancelled by this minus here. So that is going to be plus e to the minus pi psi over 1 minus psi square divided by square root 1 minus psi square times sine phi. And sine phi is square root 1 minus psi square. So these are cancelling quite conveniently again, and we end up with y of Tp is equal to 1 plus e to the minus pi psi over square root 1 minus psi square. Okay? So this is my result. This is the value of the response at this peak value. This is y of Tp. Okay? And now what I have to do is in order to be able to calculate the percent overshoot, for example, I need to subtract the value 1 from this. I will cancel this one, and I will divide the result by 1. Okay? And that is going to be just this number here. And this number is between 0 and 1. If I want the percentage value, I will multiply it with 100%. Okay? So MP, if I write this result here, is e to the minus pi psi over square root 1 minus psi square. This is my absolute overshoot formula for the case of second order system in standard form. And what about the percent overshoot? It is the same number, e to the minus pi psi over square root 1 minus psi square times 100%. Okay? This is the percent overshoot. This formula is only valid when you have a second order system in standard form. Okay? No scaling. Okay? But this formula is valid everywhere. Even if you have a scaling, so this formula is independent of that scaling, and that is going to be what we are going to be using when we have a system, when we have a second order system not in standard form. So here the only thing that I'm going to write here is going to be this. So when you write MP, you can do it to both formulas. I have e to the minus pi psi over 1 minus psi square, and I have here times 100%. Now instead of this value here, I can write e to the minus pi over tangent phi, okay, times 100%. Okay? Because tangent phi is this ratio, and here I have pi over this ratio, which gives me e to the minus pi over tangent phi, and I have times 100%. So now the only thing remaining, we have found also the relationship for the maximum overshoot. The only thing remaining for us to find the relationship is the settling time. And that is going to be actually probably the most difficult one. Before I start with the settling time here, I want to show you that the maximum overshoot is only dependent on this damping ratio. It is not dependent on any of the frequencies. It doesn't depend on the undamped natural frequency or damped natural frequency. So the maximum overshoot is only dependent on the damping ratio and no other quantities. Or you can say that because this damping ratio is determining this angle here using these formulas, then the maximum overshoot is only dependent on this angle that the poles have, or the damping ratio. Okay? And finally we have the analysis of settling time. Okay? Remember, in the case of settling time, I need to draw here some regions. So it is a 5% region, which is going to be something like this. So here, this value is, maybe I should erase the pole locations here. So this value is y infinity. So this value is going to be 1.05 times y infinity. When y infinity is 1, this is going to be 1.05. And I have 0.95 times y infinity. Okay? This is going to be the 0.5. This is going to be the 5% region for the settling time. And I need to also define the 2% region. And it's going to be a region given like this. My drawing might not be up to scale, sorry for that. So 0.98 y infinity here and 1.02 y infinity. This is a 2% region. And the settling time is defined as the time instant at which our response enters one of these regions and it never leaves afterwards. Okay? So this is going to be my settling time 5%, and this is going to be my settling time 2%. Okay? So how can we find these settling times? The first thing that I'm going to do here is that I will define the settling time in a mathematically meaningful way. So let us write Ts, the settling time. It is going to be the smallest time instant is the smallest time instant Ts such that now I need to write the condition here. The smallest time instant Ts such that I will write y of t minus I will have y of infinity is smaller than here either 0.05 y infinity, or I would have 0.02 y infinity. Okay? And this should be true for all t larger than or equal to ts. So this is the definition of the settling time. What does it say to us? It says to us that the absolute value of the difference between y of t and y infinity should be smaller than 5% of y infinity or 2% of y infinity for all time instants larger than or equal to ts. Okay? Here I can put also equality. It really doesn't matter. So here, what are those ts values? I'm looking for the smallest such ts value. For example, if I take such a ts value, then I know that the difference between the response and the final value is always inside the 5% band, and it is also inside the 2% band to the right of that ts value. Okay, so why not use such a ts value? Or at this ts, I know that the difference between the response and the final value is always smaller than the 5% or 2% of the final value. Okay, so there are infinitely many such ts values which are satisfying that condition. But here I'm looking for the smallest such ts value for each of the percentages there. Okay, there are infinitely and if I find my settling time value, any larger value than that settling time value would satisfy that inequality. Okay? I am trying to look for the smallest settling time value ts that would satisfy these conditions. These conditions are satisfied by infinitely many ts values. Okay? And I'm looking for the smallest such ts value to find my settling time. Okay? So in order to be able to find the settling time exactly, I need to find these intersections. Okay? So you see that I need to find these intersections in order to be able to find the exact settling time value. Unfortunately, this is not possible. Actually, my battery is going out, so I'm running out of battery in my microphone, so I will change it and will come back. Sorry. Okay, I'm back with the new battery. So sorry for the interruption. So as I told you, it is not possible to find these intersections. Okay? So you need to use a computer in order to be able to find those intersections, and it would be really useless to analyze the response analytically. Okay? So here we are going to follow a different approach here. The first thing that I'm going to do is that I need to substitute in that equation y infinity equals to 1. Because in our response there, but our results are going to be valid for any y infinities. So in this case, I have y infinity equal to 1, and I would have y of t minus 1 should be smaller than or equal to either 0.05 or 0.02. Okay? I need to find the smallest time instant such that these equations are satisfied for all t larger than or equal to ts. I need to find smallest such ts value. Okay? Now here's what I'm going to do. I'm going to try to find, so since I really do not want to find these intersections, instead I'm going to try to work with a simpler function than this response. So the question here is that, can I find some lower bound and some upper bound for this response? Okay, and the answer is going to be yes here. If I look at this function, I can actually find a lower bound for this response, and I can also find an upper bound for this response. How can I find the analytical expression for such upper and lower bounds? So, I'm actually going to be using this analytical formula here. I know that sine omega dt plus phi is between -1 and 1 for all t values. Okay? So if I would like to find such upper and lower bounds, I need to get rid of the sign oscillations here. We see that these lower and upper bounds do not oscillate. Okay? So from this expression, I need to get rid of that sine function, and I'm going to get rid of that sine function either by substituting sine equals to 1 or sine equals to -1, the maximum and the minimum value of the sine function. Let me try to first find the upper bound of the response, okay? So I have 1 minus, at which sine value this response becomes at its maximum, okay? At which value for this sine function this response becomes at its maximum. There is a minus sign here, therefore I need to make the sign as small as possible in order to be able to get a larger value than the function. If I want to find an upper bound for the function here, then I need to maximize this right-hand side by replacing the sine function with a constant value. And what should be the value of the sine in order to be able to maximize the right-hand side? The sine should be at its minimum. It should be at -1. So I have this -1 cancels this -1, and I would get 1 plus e to the minus psi omega n t divided by 1 minus psi square. Okay? This is exactly this upper envelope of this response. Okay? It is always larger than 1, and it is decreasing in time without any oscillations. So this upper bound is always larger than or equal to this response, the actual response y of t. Okay? And what about the lower bound? Y of t is larger than or equal to, I need to get a smaller number than the response which is not oscillating. So I need to replace this sine function with its maximum value to minimize the right-hand side in this case. And in that case, I will substitute sine equals to 1, which is going to give me 1 minus e to the psi omega n t over 1 minus psi square. So this is the upper envelope of the response. And this is the lower envelope. And actually they should be symmetric. So in my figure they are really not looking like symmetric, but they should be symmetric because this is 1 plus a quantity and 1 minus a quantity here. Okay? So now the idea to find the settling time is to find the intersection of this envelope here with the percentage boundaries. Okay, if I find the envelope intersection with the 5% boundary and with the 2% boundary, these intersections should be at the same point. Sorry for my bad drawing here. It should be something like this. So if I find the 2% intersection and if I find the 5% intersection of these boundaries with this envelope function, then I will guarantee that the actual response is actually going to remain inside the individual percentage boundaries here. If I guarantee that this envelope of the actual response is inside the 2% region, I guarantee that the actual response is inside the 2% region. Similarly, if I guarantee that the envelope is inside the 5% region, I guarantee that the actual response is inside the 5% region. Okay, so therefore, in order to instead of finding the intersection of the actual response with the 5% or 2% regions here, we are going to be finding the intersection of the response envelope with the region boundaries here, okay? And those intersections are going to give us the settling time values for the 2% and 5% settling times. All right? So here is what I'm going to do. I will modify both of these equations in the following way. So remember here, our equation to satisfy is y of t minus 1, absolute value should be smaller than or equal to 0.05 or 0.02. Okay? Now I will take these ones to the left-hand side. So I will get y of t minus 1 is smaller than or equal to a positive number, e to the psi omega n t, divided by 1 minus psi square. And I have y of t minus 1 coming from the second equation is larger than or equal to minus e to the minus psi omega n t divided by 1 minus psi square. Okay? So I see that the difference between y of t and this final value turns out to be always smaller than this decaying exponential. And y of t minus 1, the desired value or the final value, is also larger than or equal to the negative of that exponential. Okay? So here I need to... So here I have e to the minus psi omega n t divided by 1 minus psi square, and I have here the negative of that number, minus e to the minus psi omega n t divided by 1 minus psi square. What is the first equation telling us? It tells us that y of t minus 1 is smaller than this positive number. So the first equation tells us that our number y of t minus 1 should lie in that region. And what about the second equation? The same number should be larger than or equal to the negative of the same number. Okay? So the second equation tells us that our number y of t minus 1 is lying in that region. What is the intersection of those two regions? So if both of these inequalities are satisfied at the same time, then the absolute value of y of t minus 1 should be smaller than or equal to this decaying exponential. Okay? That is what I'm going to write here. So here, y of t minus 1, absolute value. If both of these equations are satisfied at the same time, this is smaller than or equal to e to the minus psi omega n t divided by 1 minus psi square. Okay? And you see that this is very close to the inequality that I would like. Okay? I would like such an inequality and for finding the settling time, and here I have found an inequality which is very similar, except we have a time dependent right hand side here. Okay? So here we are going to make one more approximation. This exponential really decays quite fast, and this is just a constant here. So the effect of this constant is actually cancelled by the decaying exponential quite fast. Okay? So if t increases with a very, very small amount, the exponential decreases quite fast to actually cancel the effect of this number here. So now instead of writing this one, I'm going to be writing an approximate inequality, t minus 1, smaller than or equal to e to the minus psi omega n t. Okay? So we have this approximate inequality. So now I'm asking you the following question. how should I choose? What is the smallest number? What is the smallest time t instant? Such that the right-hand side here is smaller than or equal to 0.05. Or what is the smallest time instant such that this exponential is smaller than or equal to 0.02? Okay? We have to answer that question to find those smallest time instants will be our settling times. Alright? What is the smallest time instance such that this exponential is smaller than or equal to 0.05 or 0.02? Okay? And in order to be able to answer those questions, I'm going to tell you the following facts. If you calculate e to the minus 3, this is approximately 0.05, and if you calculate e to the minus 4, this is approximately 0.02. Okay? What does this mean? So this means that if I take my time instant such that this psi omega n t is equal to 3, then the t value that would satisfy that equation would give me the smallest time instant such that this exponential is actually smaller than or equal to 0.05. Okay? Similarly, if I try to make psi omega n t equals to 4, then for all larger time instants than the time instance satisfying that equation, this exponential is going to be smaller than or equal to 0.02. So our settling times, 5% settling times and 2% settling times are going to come from equating this exponent of this exponential to minus 3 and minus 4. So let us write those. Minus psi omega n t is equal to minus 3. The solution of this equation is Ts is equal to 3 over psi omega n. And minus psi omega n t is equal to minus 4. This gives me the solution Ts is equal to 4 over psi omega n. Okay? And actually, these are going to be our approximate formulas for 5% settling times and 2% settling times. Okay? And what are these numbers? Let us try to understand. In the response, I have a decaying exponential, e to the minus psi omega n t. This is equal to, if I try to find the time constant of that exponential, if I want to find what capital T is in this equality, you would see that T would be equal to 1 over psi omega n. Okay? So the time constant of this decaying exponential is 1 over psi omega n, and 5% settling time is nothing but the 3 time constants of this response, this exponential, and the 2% settling time is nothing but the 4 times the time constant of this exponential. Okay? So these are just very approximate formulas that we can use in order to be able to make time domain analysis, in order to be able to understand the time behavior of the systems from frequency domain or from Laplace domain quantities here. So the thing that I'm going to mention is going to be, we see that here the time constant is related to this real part of the poles. So we see that the real part of the poles is minus psi omega n. Therefore, if the real part, if this distance of the poles from the origin or from the imaginary axis is large, then time constant is going to be small, and we are going to have a faster convergence or a fast. When psi omega n is large, settling time is small. That means that we will have a faster settling time. The response is going to settle faster to the desired or the final value. If the poles are further away from the imaginary axis, we're going to have fast convergence. If the poles are close to the imaginary axis, we're going to have slow convergence. Because if psi omega n is small, then the poles are close to the imaginary axis. And if psi omega n is small here, settling times would be very, very large. Okay? And in that case, we are going to have a very slow convergence to the desired value. So the settling time is related to the real parts of the poles. And I also talked about what the imaginary parts of the poles would mean, and they determine the frequency of oscillations in the underdamped case. So now we have found all of our expressions, finding the performance measures or expressing the performance measures in terms of the Laplace domain quantities. Now let me write a summary of those. So the summary is the following. So the rise time is pi minus phi divided by omega d. And the peak time is pi over omega d. We have found this. And the maximum overshoot, I will write only the percent overshoot here. E to the minus pi psi over 1 minus psi square times 100%. Or I can write here e to the minus pi over tangent phi times 100%. And we have found the settling times. Ts 5% is 3 times the time constant. And settling time 2% is 4 times the time constant. Okay? So these are our formulas. And now let us quickly solve an example or about what we can do with these relationships. Let us write an example. Two second-order systems in standard form have the following poles. Compare the systems in terms of Ts, Tr, and the maximum overshoot. So we are going to be given pole locations of two second-order systems in standard form. Okay? And the poles of the first system are given like this. So these are the poles of the system 1. And poles of the second system are given like that. Okay? So these are the poles of the system 2. Now, by just looking at these pole locations, I need to determine what would be the relationship between the settling times of these two systems and the rise time of these two systems, or the maximum overshoot of these two systems. Okay? So the first thing that I'm going to do is to make some markings here. We see that the imaginary parts of the poles are the same for these two systems. What does that mean? We know that the imaginary parts of the poles are determining the frequency of oscillations in an underdamped response. Okay? So if I try to draw the responses of these two systems, the step responses of these two systems, then the frequency of oscillations of those two responses should be the same. Okay? So I have here, maybe I should write this to the other side. So this is imaginary as. This is j omega d 1, this is at the same time equal to j omega d2. So omega d1 is equal to omega d2 for these two systems. What about the real parts? Obviously the real parts are different. Minus psi 1 omega n1 and minus, sorry, I'm making a mistake here. This is psi 2 omega n2 and psi 1 omega n1. These are the poles of the first system. So I have psi 1 and omega n1 here, this point. And here, this point is minus psi 2 omega n2. Okay? If I draw these angles, which are going to be important, I can draw them like this. So this is the angle of the second system, phi 2. This is the angle of the first system, phi 1. All right? Now, before these performance measures, TS, TR, and P here, I want to look at the basic parameters here. Damping ratio. These two systems have a damping ratio. They both have a damping ratio, and these damping ratios are not the same. What is the relationship between the damping ratios of the first system and the second system? And how can you understand the relationship between these? So here, the good thing is that we have a relationship given like this, okay? The damping ratio of a system is cosine phi, okay? And if I compare the angles phi for these two systems, phi 1 and phi 2, I see that phi 1 is larger than phi 2, okay? This is the angle of the first system is larger than the angle of the second system poles, all right? So then what is the relationship between the damping ratios of these two systems? So if an angle gets larger, what would happen to its cosine? I know that cosine would decrease. If the angle is between 0 and 90 degrees, then when the angle is increasing, the cosine would be decreasing. Okay? So the damping ratio of the first system is smaller than the second system, that of the second system. Here, you can also reason like this. So what would happen to the damping ratio if this angle was 90 degrees? If the angle was 90 degrees, the poles would be exactly on the imaginary axis. And what is the damping ratio then? It is the undamped case, and the damping ratio should be equal to 0 when the angle is 90 degrees. And when the angle is 0 degrees, then I should have a critically damped system, which means that the damping ratio is equal to 1. Okay? So as the angle goes from 0 to 90 degrees, the damping ratio is reduced from 1 to 0. Okay? So the damping ratio decreases as the angle increases here. Okay? Since the first angle is larger, the damping ratio of the first system is smaller. So what about the undamped natural frequencies of these systems? Omega n1, omega n2. So remember, when I look at the pole positions, omega n was the distance of these poles to the origin. Okay? This distance is always equal to omega n. That is what the radius of this circle is. Okay? The distance of these poles for the underdamped systems is omega n. Therefore, which pole here has a larger distance to the origin here? So I see that the poles of the second system are further away from the origin, which means that I need to have a relationship given like this. Okay? So we have calculated omega, we have compared omega n's, and omega d1 is equal to omega d2. These are the damped natural frequencies. They are equal for these two systems. Okay? So now let us look at TS. TS1 and TS2. What is the relationship between the settling times of these two systems? So the settling time would be determined by the real part of the poles. Okay? If the real part is large in magnitude, then the settling time is small. If the real part is small in magnitude, then the settling time is large. So as the poles goes from right to the left, the settling time would be decreased. Okay? Because the poles are getting further away from the imaginary axis. So the magnitude of the real parts are getting larger and larger as the poles get away from the imaginary axis. That means that the first system is going to have a larger settling time. Okay? Because psi 1 omega n1 is actually I can write this one, psi 1 omega n1 and psi 2 omega n2. Which one is larger in which system? I see that this distance is psi 1 omega n1 and this distance is psi 2 omega n2. That means that the second system has larger psi 2 omega n2, and that means that the second system has a smaller settling time. So what is next? The rise time. TR1, TR2. All right? In this case, the rise time is dependent on two quantities, phi and omega d. Okay? And we see that omega d's of these two systems are the same. These are the same for both systems. So the difference between the rise times would depend on phi only. Okay? The phi of the first system is larger. That means that the rise time of the first system would be smaller. All right? And finally, I come to the maximum overshoot. So I'm P1 and P2. I know that the maximum overshoot is only dependent on the damping ratio or the angle of the poles here. So here, these are the expressions. So I have the damping ratio relationship given like this and the angle relationship given like this. If you try to use, in my opinion, if you try to use these expressions, you are going to almost always make a mistake. Okay? Because when phi gets larger, tangent gets larger, then this ratio becomes smaller. When this ratio becomes smaller, there is a minus sign, exponential becomes larger, etc. Or when psi gets larger, what is happening to this ratio, etc. It's really the relationship that we have found is really complicated here. So then how should I decide which maximum overshoot is actually larger? You need to think about the limits, okay? What happens when this angle becomes at the 90 degrees? In that case, I would have just the undamped case, and in the undamped case, I have the largest maximum overshoot, okay? As the angle gets larger, and when it comes to 90 degrees, I have the maximum overshoot. And what happens when the angle is small, very close to zero? In that case, I have a critically damped system. It is no longer oscillatory. The response is no longer oscillatory, and therefore the response does not have any maximum overshoot. So therefore, when this angle is small, then I would have zero maximum overshoot. When this angle is large, then I have the largest maximum overshoot. Okay? So which means that the system with the larger angle is going to have the larger overshoot here. Okay? So since phi 1 is larger than phi 2, we have a larger maximum overshoot for the first system. So now you see that I have actually completed. So this is what time domain analysis is. By just looking at the frequency domain or the Laplace domain So here I need to make a correction. I am always saying that frequency domain because in electrical engineering, frequency domain, there is something called frequency domain, and it's very close to the Laplace domain that we are using. But here in this course, I should not use frequency domain because those ideas were not introduced to you. So here I need to only say that we are dealing with the Laplace domain quantities. So whenever I say frequency domain, I'm making a mistake in this course. So please replace that phrase in your mind with the Laplace domain. Okay? Because we are using it very, very commonly in electrical engineering, I am always making that mistake, and that disturbs me. Sorry, and I hope it doesn't disturb you. So here, by looking at the pole locations, we can say something about the time domain quantities. So here is what I'm going to try to do. By just looking at those pole locations, I will try to draw the step responses of those two systems. Okay? So I would have the time axis here, and this is my step function. And here, what are these relationships telling us? So the first thing is that the first system is going to have a smaller rise time. Suppose that the rise time of the first system is here. So I have TR1 here. And suppose that the rise time of the second system is here, TR2. Okay? And what about the maximum overshoots? Before the maximum overshoot, let me write the relationship between the TPs. TP, peak one, the first peak one, and the second peak one. Peak time. So what is the relationship between the peak times of these two systems? So remember the formula for the peak time. TP is pi over omega d. Okay? So peak time is only related to the imaginary part of the poles, and for these two systems, the imaginary parts are the same. That means that the peak times of these two systems should be the same. Okay? And here is what I'm going to do. I'm going to mark a peak time here. So this is the peak time of the first system, TP1, and the second system, and this is the peak time of the first system, TP2. They are exactly at the same point. And the maximum overshoot of the first system is larger. So let us say that this is the maximum overshoot this is the peak of the first system. And the second system has a smaller maximum overshoot, like this. All right? And what about the settling times? Settling time of the first system is larger. That means that if I try to draw the envelope of the first system, it is going to decay very, very slowly. The envelope is going to be something like this. And if I try to draw the envelope for the second system, then its envelope would be getting small quite quickly. Okay? Let us say that it's something like this. All right? Now, if I try to draw these responses, the response for the first system is going to, here it is rise time, which is smaller than the rise time of the other system. And then it's going to make a maximum overshoot. And then it's going to continue oscillating like this. Okay? And what about the second system? The second system is going to start here. The rise time will hit the maximum, and then it's going to the oscillations will get smaller and smaller very, very quickly, because its settling time is smaller than the first system. So we see that by just looking at the Laplace domain quantities, these pole locations, psi, omega n, omega d, etc., these pole locations, we can say really a lot about the step responses of these two systems. That was the main aim of the time domain analysis, making a relationship between Laplace domain quantities and the time responses, which we have already done. So I'm going to give you an exercise and then finish this lecture. So suppose that I change, in this example, suppose that I change my pole locations to the following one. Okay? So suppose that these are the pole locations for S1, and suppose that these are the pole locations for S2. So they are on the same line here, okay? And S2 poles are here and S1 poles are here, but they are on the same radial lines here. Repeat this example for such a case. And also another exercise might be, suppose that my pole locations are like this. This is the pole locations of the first system. So this is for S1 and this is for S2. In this case, the real parts of the poles of the systems are the same, but the imaginary parts are different. So repeat this example for these pole locations instead of the original ones that we started with. So I'm going to stop here and then we'll continue with the third lecture. Thanks for watching.